Database normalization is like organizing a messy room. Just as you would sort items into proper places to avoid duplicates and make things easier to find, normalization organizes database data to reduce redundancy and improve integrity. Imagine you have a messy room with books and clothes scattered everywhere. It's hard to find what you need, and you might have duplicate items in different places. After organizing, books go on the bookshelf and clothes go in the closet. Everything has its proper place, making it easier to find and maintain. Database normalization works the same way. Instead of having data scattered and duplicated across tables, we organize it systematically to eliminate redundancy and improve data integrity. Here's an example of an unnormalized database table. Notice how customer information like name and address is repeated multiple times for different orders. The red highlighting shows redundant data. John Smith's address appears twice, and Jane Doe's address also appears twice. This redundancy creates several problems. This redundancy leads to three main types of data anomalies that normalization helps prevent. First, insertion anomalies occur when you cannot add certain data without having other unrelated data. For example, you cannot add a new customer to this table without also adding an order. Second, update anomalies happen when you need to change the same information in multiple places. If John Smith moves, you must update his address in every row where it appears. Third, deletion anomalies occur when removing data unintentionally eliminates other important information. If you delete a customer's only order, you also lose all their contact information. Database normalization solves these problems by organizing data into separate, related tables that eliminate redundancy while maintaining data relationships. Normalization provides 5 key benefits for database design. It eliminates data redundancy by storing each piece of information only once. It improves data integrity by ensuring consistency across the database and prevents the data anomalies we just discussed. Additionally, normalization reduces storage space by eliminating duplicate data and simplifies data maintenance by centralizing information updates. In summary, database normalization is a systematic approach to organizing data that creates more efficient, reliable, and maintainable database systems. It's the foundation of good database design. First normal form, or 1NF, is the foundation of database normalization. The core principle is simple but crucial. Every cell in your table must contain atomic values. An atomic value means indivisible. It's a single piece of data that cannot be broken down further. For example, a single name like John is atomic, but a comma-separated list like John, Jane is not atomic. Here's a typical problematic table that violates first normal form. Notice the courses column contains multiple values separated by commas. This creates several serious problems. This structure creates multiple problems. It's hard to search for students taking a specific course, difficult to count total enrollments, and nearly impossible to efficiently add or remove individual courses. To fix this, we apply first normal form by creating separate rows for each course. This ensures every cell contains only atomic, indivisible values. Here's our table after applying first normal form. Each course now has its own row, and every cell contains exactly one atomic value. Notice how Alice, who was taking 3 courses, now appears in 3 separate rows. This normalized structure provides immediate benefits. We can now easily search for all students taking a specific course, count total enrollments accurately, and efficiently update or delete individual course records. Remember these key rules for first normal form. Each cell must contain only one atomic value, avoid comma-separated lists, create separate rows for multiple values, and this foundation enables all future database operations to work efficiently. Second normal form, or 2NF, builds upon first normal form by eliminating what we call partial dependencies. But what exactly is a partial dependency? A partial dependency occurs when a non-key attribute depends only on part of a composite primary key, rather than the entire key. This creates redundancy and potential data inconsistencies. Here's a student enrollment table that violates second normal form. Notice we have a composite primary key made up of student ID and course ID together. The composite primary key consists of both student ID and course ID. Together, these 2 columns uniquely identify each enrollment record. Here's the problem. Student name depends only on student D, not on the full composite key. Alice is Alice, regardless of which course she's taking. This creates a partial dependency. This partial dependency causes redundancy. Alice's name is repeated in multiple rows, which wastes space and can lead to update anomalies if we need to change her name. To achieve second normal form, we need to split this table into two separate tables, removing the partial dependency. We create two tables, a students table where student name depends fully on student ID, and an enrollments table where grade depends on the full composite key of student ID and course ID. Now each table has proper dependencies. In the students table, student name fully depends on the primary key student ID. In the enrollments table, grade fully depends on the composite primary key of student ID and course ID. Here are the key takeaways for second normal form. A table must first be in one NF, then all non-key attributes must depend on the entire primary key, not just part of it. This eliminates partial dependencies, reduces redundancy, and may require splitting tables to achieve proper normalization. Third normal form takes database normalization one step further by eliminating transitive dependencies. A transitive dependency occurs when a non-key attribute depends on another non-key attribute rather than directly on the primary key. In a transitive dependency, we have a chain where the primary key determines one attribute, which in turn determines another attribute. This creates an indirect relationship that violates third normal form. Here's a student table that violates third normal form. Notice how advisor name and advisor office depend on advisor ID, which in turn depends on student ID. This creates redundancy and potential update problems. The transitive dependency chain is clear. Student ID determines advisor ID, and advisor ID determines both advisor name and advisor office. This means advisor information is repeated for every student with the same advisor. To achieve third normal form, we split the original table into two separate tables. The students table contains only student information and the advisor ID as a foreign key. The advisors table contains all advisor-specific information. This eliminates the transitive dependency because advisor information now depends directly on the advisor ID primary key in the advisors table, not indirectly through the students table. Third normal form ensures that every non-key attribute depends directly on the primary key, eliminating transitive dependencies. This creates a cleaner database structure with less redundancy and fewer opportunities for data inconsistencies when updates are made. While third normal form handles most database design needs, there are situations where even higher levels of normalization become necessary. Today, we'll explore 3 advanced normal forms that address specific data integrity challenges. Boyce-Codd normal form, or BCNF, is a stricter version of third normal form. It addresses problems that can occur when a table has overlapping candidate keys, multiple sets of columns that could serve as primary keys. Here's an example. Consider a table storing information about professors, courses, and textbooks. A professor can teach multiple courses, and each course can have multiple textbooks, but each professor uses specific textbooks for their courses. This table violates BCNF because professor and course together determine textbook, but professor alone also determines which textbooks they prefer. This creates overlapping dependencies that can cause update anomalies. Fourth normal form addresses multi-valued dependencies. This occurs when one attribute determines multiple independent sets of values. For example, a student can have multiple hobbies and multiple skills, but these are independent of each other. Here's a problematic table where students have both hobbies and skills. Notice how John appears multiple times with different combinations, creating unnecessary redundancy and potential inconsistencies. To achieve fourth normal form, we split this into 2 separate tables, one for student hobbies and another for student skills. This eliminates the multi-valued dependency and reduces redundancy. Fifth normal form, also called project join normal form, deals with join dependencies. This is the most complex normal form and is rarely needed in practice. It ensures that a table cannot be decomposed into smaller tables without losing information. Fifth normal form typically applies to complex many-to-many-to-many relationships. For example, consider suppliers, parts, and projects, where a supplier can supply specific parts to specific projects, but not all combinations are valid. Here are the key takeaways about higher normal forms. Most databases only need third normal form. BCNF is used when you have overlapping candidate keys. Fourth normal form handles multi-valued dependencies. Fifth normal form is rarely needed but addresses complex join dependencies. Remember, higher normalization isn't always better. It depends on your specific requirements. Denormalization is the intentional process of adding redundancy back into a normalized database to improve query performance. While this might seem counterintuitive after learning about normalization, it's a strategic decision that can significantly boost database performance in specific scenarios. At its core, denormalization means deliberately storing the same piece of information in multiple places within your database. This creates redundancy, which we normally try to avoid, but it can dramatically speed up queries that would otherwise require complex joins. Let's look at a practical example. Imagine we have a normalized e-commerce database with separate orders and order items tables. In the normalized version, to get the total for an order, we must calculate it by summing all the item prices. To find the total for order 1, we need to query the order items table, sum up 800 plus 20, and get $820. This requires a join operation and calculation every single time we need the order total. Now let's see the denormalized version. Here we store the order total directly in the orders table. This creates redundancy because the total could be calculated from the order items, but it eliminates the need for complex queries. Denormalization is most beneficial in read-heavy scenarios. If your application performs many more select queries than insert, update, or delete operations, the performance gains from denormalization can be substantial. However, denormalization comes with important trade-offs. While it improves read performance, it can slow down write operations because you need to update multiple locations when data changes. It also increases storage requirements and the risk of data inconsistency. Here are the key takeaways about denormalization. It's a strategic tool that should be used thoughtfully, not as a default approach. Consider your application's read-to-write ratio, performance requirements, and maintenance capabilities before implementing denormalization. The choice between normalization and denormalization isn't always clear-cut. As a database designer, you need a systematic approach to make this critical decision based on your specific requirements. Let's start by understanding what each approach prioritizes. Normalization focuses on data integrity, eliminating redundancy, and ensuring consistent updates. It's all about maintaining clean, reliable data structures. Denormalization, on the other hand, prioritizes query performance and faster reads. It accepts some redundancy in exchange for simplified queries and reduced joins, making it particularly suitable for analytics workloads. Now let's examine the key factors that should guide your decision. First, consider your read-to-write ratio. If your application performs many more reads than writes, denormalization can significantly improve performance. Data volume is another crucial factor. Large data sets with complex queries often benefit from denormalization to avoid expensive join operations that can slow down performance significantly. Consider your consistency requirements. Applications that require strict data consistency, like financial systems, typically need normalization to prevent data anomalies and maintain integrity. Finally, evaluate storage costs. If storage is expensive or limited, normalization helps eliminate redundancy and reduces storage requirements, though it may impact query performance. Let's look at two contrasting examples. A banking system requires strict normalization because data integrity is paramount. Account balances must be accurate, transactions must be consistent, and regulatory compliance demands reliable data structures. In contrast, an analytics dashboard benefits from denormalization. It handles read-heavy workloads with complex aggregations where query performance matters more than perfect consistency. Historical data analysis can tolerate some redundancy for faster insights. Here's a practical decision framework you can use. This matrix provides clear guidelines based on common scenarios you'll encounter when designing database systems. Remember these key takeaways when making your decision. First, this isn't an all-or-nothing choice. You can use both approaches in different parts of your system based on specific requirements. Consider your system type. OLTP systems that handle transactions typically favor normalization, while OLAP systems designed for analytics often benefit from denormalization. Finally, database design is an iterative process. Monitor your system's performance and be prepared to refactor as your requirements evolve. The right choice today might need adjustment tomorrow. Now that we understand normalization and denormalization concepts, let's explore the best practices for applying them in real-world database design scenarios. The first and most important best practice is to always start with a normalized design. Think of normalization as your foundation. It ensures data integrity and eliminates redundancy from the beginning. Only after you've identified specific performance bottlenecks should you consider denormalization. This selective approach ensures you maintain data integrity while optimizing only where necessary. Documentation is crucial in database design. Every normalization and denormalization decision should be documented with the reasoning behind it. This helps future developers understand the design choices. Database views are an excellent tool for providing denormalized access patterns without altering your underlying normalized structure. Views act as a bridge, giving you the best of both worlds. Let's look at a real-world e-commerce example. Order processing typically remains normalized because it requires strict data consistency for financial transactions and inventory management. However, product catalogs are often denormalized for faster searching and browsing. Since product information changes less frequently, we can trade some storage space for much better query performance. In modern database systems, we also need to consider NoSQL databases and data lakes, where denormalization is often more prevalent due to their document-oriented or schema-less nature. Let's summarize the key takeaways for database normalization best practices. These principles will guide you in making informed decisions about your database design. Remember, database design is not a one-time decision. As your application grows and requirements change, you may need to revisit your normalization strategy. The key is to make informed decisions based on actual performance data and business needs.